Hello team. Today we're going to have a look at electrical legislation, standards and codes. So by now you should have a rough working knowledge of the Electricity Act and the Electricity Safety Regulations. We are going to look at those very briefly at the start of this module, but we're not going to go into detail on those. If you need to refresh yourself there, please go back to the previous topics and have another look at ones we've already done. So today we're mostly going to focus on the standards and specifically we are going to look at the two standards we use the most often, which will be AS/NZS 3000, which is the wiring rules or electrical installations, and AS/NZS 3760, which is appliance testing and certification. I would encourage you as we go through this video to have those documents open, AS/NZS 3000, AS/NZS 3760, so you can refer to what I'm talking about. I will bring them up on the screen when we need to look at specific things. But if you have them open as well, if you've got the possibility of having them open side by side with this video, then that will make your life a little bit easier. You will find the links to those pieces of legislation on the Canvas page for this topic. So there's links for the Act, the regs, and those two standards in there as well. So you can click on those at any time, download them or view them. You'll be able to use those throughout the course. You can always refer back, and this is where you will find those two pieces of legislation. So let's get into it. Electricity Safety Regulations 2010. They came into force in 2010 to revoke the 1997 regulations. They promote the health and safety of the public and prevention of damage to property in connection with the use, supply and use of electricity in New Zealand. So what do? They gather together and state generic rules about electrical safety and what's deemed to be electrically safe and unsafe. Again, remember that this is generic. If we're looking for specific rules, those are going to be in the standards, usually in AS/NZS 3000, because that's the general wiring rules, and that will cover the vast majority of work that we do. However, for specialist applications, specialist types of electrical work, there may be specific standards for those. We're not going to cover those standards today. Those have separate topics and modules later on in the course. So regulations are general and generic rules. Standards are more specific. The regs deal with the design, construction, use and works, use of works, installations, fittings and appliances. Works, remember, anything connected with the transmission of electricity, like power lines, substations, that kind of thing. Installations being the buildings that electricity is used in, houses, whatever. Fittings are the things that are screwed to the wall, switchboards, power points, light switches, that kind of thing. And then appliances are anything we plug in. They deal with the importation and sale of fittings and appliances. Remembering that when we import stuff from overseas, there must be some method of ensuring that those are safe and approved for use in New Zealand. They provide for installations to be designed and installed under AS/NZS 3000. So the regulations give us, they reference the standard, and that gives us the authority to use that standard as a means of complying with the regulations. So the regulations will tell us that everything needs to be safe, but it's general. It doesn't tell us how to do that. So it says go and have a look in AS/NZS 3000. That's where you get that specific information. So the regs refer to that standard. The regs define the requirements relating to safety management systems. They set out in schedules all the standards applicable to the regulations. That means that it lists in the schedules which standards that are able to be used, with a focus on the adoption of international standards, and provides for offences including infringement offences. So that tells us if you do this or that, that's illegal, and here's what could happen, a fine or what have you. So how it all works: the Electricity Act is the governing document. The Electricity Act is created in and approved by Parliament. The Act then directs us to the Electricity Safety Regulations, which contain the legal requirements to allow us to comply with the law, to comply with the Electricity Act. And then the standards give more detailed requirements that help us comply with the regulations. And here we have it here. So the Act sits at the top, that hands down to the regulations, and then the regulations hand down to the standards. As I said, we'll primarily use ASNZS 3000, also 3760, but any other standard that we might use would be included here. And then we also have the codes of practice, which the codes of practice predate the standards. The ASNZS 3000, for example, was first adopted or introduced in the year 2000, I believe. And the most of the electricity codes of practice, which existed before, were then revoked, and now we use the standard. However, some of those codes of practice still exist. Well, I don't think we're going to go into much detail on that today, but it's worth noting that some of those, for specific purposes, still exist. So the scope of ASNZS 3000. This standard sets out the requirements for the design, construction and verification of electrical installations, including the selection and installation of electrical equipment forming part of such electrical installations. These requirements are intended to protect persons, livestock and property from electric shock, fire and physical injury hazards that may arise from an electrical installation that is used with reasonable care and with due regard to the intended purpose of the electrical installation. In addition, guidance is provided so that the electrical installation will function correctly for the purpose intended. All that is telling us is that ASNZS 3000 is here to give us guidance on how to design, construct and test electrical installations in order to make sure that people using them in a normal manner, not people who want to go in and fiddle with stuff and pull things to bits and modify it, but if people are using those installations in a normal manner, then they should be protected against personal injury such as electric shock or property damage. Part 1 provides uniform essential elements that constitute the minimum regulatory requirements for a safe electrical installation. Part 2 provides installation practices that achieve certainty of compliance with the essential safety requirements of Part 1. So it's worth noting here that the difference between Part 1 and Part 2. So Part 1 gives us some really general rules, really general minimum rules. Part 2 is more detailed. Part 2 is where it goes into how we, for example, select which cable we need to use, how we decide how we're going to build our switchboard, what kind of circuit breakers we need to use, what the ratings of those things should be. So Part 2 is the one that we normally deal with because it is the most detailed information. Now, what Part 1 does is allows us, if there is a very good reason why we need to construct our electrical installation in such a way that it's not complying with Part 2, so we might do something that's different to what's in Part 2, those detailed instructions. Part 1 tells us that as long as we design it in a safe manner and we can prove that it is safe even though it may not meet those requirements for Part 2, then that is okay. In saying that, however, the vast majority of the work that we would do will be under Part 2, those detailed rules. Part 1 is usually used if we were going to do something that didn't comply with Part 2. Part 1 would be used for a very specific scenario. I don't think I've ever done one myself where I've been involved with the construction of a installation that it does not comply with Part 2 and only complies with Part 1. So most of the time we don't have to worry about Part 1. If you ever come across this in the future, you're going to need some more detailed information about that. For the vast majority of cases, we can just worry about what's in Part 2. So let's just put a pause on this presentation here and go and have a quick look at that standard itself. So here it is here. As I said, we've got a link to this on our Canvas page. You can see that there. All of these blue ones here are our links, and this one here, ASNZS 3000, is what we're looking at now. Oh, it's the wrong one. This one here. Okay, so I'm just going to scroll straight down to the to the table of contents, and we'll have a quick look here. It's worth noting here that most of these standards, all bar one I think that I've come across, are all generally laid out in the same way. So if we get familiar with how this document is structured, the structure would be substantially the same across all of the different standards that we use. So if we start here with section 1, so scope application of fundamental principles. Fundamental principles there being, that's what we would look at if we were going to do, as I said, we're not going to comply with part 2, we're just going to come up with our own design. We would look at those fundamental principles. But let's, for now, we'll have a look at the scope and definitions. Scope is 1.1. Again, in all standards, essentially, we have the scope is going to be 1.1. The scope tells us what this document covers. So it's always a good place to start. If you're not sure what standard you should be looking at, like if I need to do this thing, is it this standard, is it this standard? We can get those standards and have a look at the scope, and that should give us a clue as to what's covered by that document and whether the work that we're going to be doing falls under that standard or not. 1.4 in all of our standards is going to be definitions. Apologies for my poor highlighting there, definitions. And generally, as I said, 1.4 will be definitions. Again, this is where we find information or definition of specific words or phrases that may be used within the standard. And those are usually there if there may be a word or a phrase that has a general usage meaning, but in relation to this document in particular, it has a specific meaning. So if you're ever going through one of these documents and it says something, a word or a phrase in a context that you're not used to or you don't know what it means, definitions is the place to look. So let's start with the scope then. Scrolling down. Here it is here. So the scope is, as we just read on that last slide. So if you look at that there, that tells us all of the things that are going to be covered in general in this document. If we scroll down a bit, we get to section 1.4, as I just said, definitions, and we can see definitions of specific words. So for example, the very first one here, accessible, readily. So readily accessible. So throughout the document, it may refer to readily accessible. It might say, for example, that all isolation switches for machines must be readily accessible. Now that would contain a fairly general or generic definition if most people read that. But in relation to this, if we were talking about isolation switches must be readily accessible, each individual, one of us, might have a slightly different definition of what that means. Does that mean that everybody has to be able to reach it? Can I put it in a cupboard? What about if I needed a ladder? Well, it's still accessible, but I just need a ladder. So we could then theoretically get into arguments or do work that may not meet the requirements of readily accessible if we come up with our own special version of what readily accessible means. So in this case, the document tells us what readily accessible means. It says capable of being reached quickly and without climbing over or removing obstructions, mounting upon a chair or using a movable ladder, and in any case not more than 2 meters above the ground floor or platform. Okay, so it's really specific there. So it says that readily accessible means that we shouldn't have to climb over anything or getting rid of stuff or getting up on a chair or using a ladder, and it's not more than 2 meters above the ground. So it tells us what that means. Even though readily accessible might be, as I said, a fairly generic concept, the document defines. So more than happy for you to read through that on your own time. I'm certainly not going to go through every single definition which is within this, but might be a good idea just to scan through that and get a rough idea of what sort of things are going to be covered by the definitions in this document. And it's always a handy place as well to get a feel for the document, because it's going to talk about all of those specific concepts, words and phrases, so we can start to get an idea of the types of things that are going to be covered in this document by what it decides we need to define. So let's go back here. Okay, the application. This standard may be applied through legislative requirements made in each state and territory of Australia and in New Zealand concerned with the safety of electrical installations. The standard may also be applied in conjunction with any additional requirements, exemptions or restrictions in such legislation. The principal application of the standard is to electrical installations in all types of premises and land used by electricity consumers. Let's give it roughly. It's saying that the standard may be applied through legislative requirements. That means that the legislation, in this case the electricity safety regulations, tells us to go to AS/NZS 3000. So here are two parts: scope, application, fundamental principles, and then part 2, installation practices. So that's sections 2 to 8. So part 1 is section 1, part 2 is sections 2 to 8, and I described what the difference between those two is before. So section 1, part 1, which is section 1 of the standard, provides a mechanism for acceptance of design and installation practices that may not be addressed by those given in part 2. So again, just so we really get that into our heads, part 2 tells us all of the stuff that we need to do. Sometimes we might need to do something that's not covered in part 2, so we refer back to part 1 for the generic rules. We come up with our own design, prove that it is safe, and then we can use that. Again, we don't generally do that. The vast majority of what we do would just be covered by part 2. And as it says there, for part 1, this mechanism is only intended to apply where departures from the methods in part 2 are significant. Section 2, general arrangement, control and protection. The provisions of section 2 form the minimum standard in relation to the selection of installation of switchgear and control gear that must be achieved to satisfy part 1 of the standard. So let's have a quick look at that. If I scroll down until I find what's going on here, my computer is opening random things. So scrolling down through definitions. A lot of definitions. So we get to part 2, installation practices. In section 2, which is the first section in part 2, tells us about the selection and installation of switchgear and control gear. So that would be our all the stuff that's inside a switchboard. When we say switchgear and control gear, we mean circuit breakers, main switches, RCDs, that kind of stuff. And then obviously that section has various subsections. So it's talking about here, what have we got? 2.2.1.2 common neutral. And it tells us the rules for common neutrals. 2.2.2 is maximum demand. The maximum demand in consumers' mains, sub-mains and final sub-circuits, taking into account the physical distribution and intended usage of electrical equipment in the electrical installation and the manner in which the present requirements might vary, shall be determined by one of the methods set out in items A to D. So what is maximum demand? Maximum demand means how much power is this electrical installation going to consume at any given time? What's the most that it will ever use? Because when we use that to decide how big our cables need to be, how big our main switches need to be, all of that kind of stuff, because all of those things are defined by how much current I'm going to carry or how much power we're going to be using. So the more power I use, the bigger the cables will need to be, so on and so forth. Hopefully that makes sense. So this clause here gives us a way of calculating what the maximum demand will be. Because as you can imagine, if I just said to you, here's an installation, tell me what the maximum demand is, well, I don't know what's in there. How is it going to be used? This section tells us how we can calculate that. Now, we'll go into that in much more detail later. In different modules, we go through maximum demand, but we can see here that, so this is one of the ways that the standard defines how we do things and what we can and can't do. It's going to show us how we define maximum demand, for example. So that's section 2. Section 3, selection and installation of wiring systems. The provisions of Section 3 form the minimum standard in relation to the selection and installation of wiring systems that must be achieved to satisfy Part 1 of the standard. So if I scroll all the way through Part 2, so you could tell everything that's included in that, whether it's in section 2, because it says it there. 2.3.3 means section 2, paragraph 3, subparagraph 3. So we're going to scroll down until we find section 3. Scrolling. My apologies. Goodness, I should find a better way of doing this, shouldn't I? Here we are. So here we are, section 3, selection and installation of wiring systems. So this is going to give us the rules around how we decide what cables we're going to use, basically. So the previous section, section 2, talked about how we decide what sort of fittings we should use, how big they should be, all of that kind of stuff. Section 3 tells us the same about cables and wiring. So depending on the usage and the location and all of that kind of stuff, what wiring do I need to use? We have it here, protection against physical contact with live parts by durable installation materials or placing live parts out of reach, satisfying the current carrying capacity, voltage drop and other minimum size requirements for conductors, so on and so forth. So this tells us all of the things that we need to take into account when we're selecting what cables we're going to use and then how we make that determination. Section 4 is the selection and installation of appliances and accessories. I won't go back to the document for the remainder of these remainder of the slideshow because it's just going to take me ages to scroll through things. Again, please do go and research this yourself. When we're doing these video lectures, it really is going to be a requirement for you guys to take control of your own learning and spend some time digging into these things a little bit more. Anyway, so section 4, selection and installation of appliances and accessories. The provisions of section 4 form the minimum standard for selection and installation of appliances, accessories and other electrical equipment not specifically covered in other sections of part 2 of the standard. So this tells us how we decide what appliances and accessories we would use, how we are going to install them, what the requirements for those things might be. So it's going to have things in there like ovens and how we connect an oven that might be different to other appliances, all of that kind of stuff. Section 5 is about earthing arrangements and earthing conductors. So it provides the minimum standard for the selection and installation of earthing arrangements. So earthing is our main earth, stake outside the building. It'll cover the cable that will run from that earth stake into the switchboard, how we connect all our earths in the switchboard, how the earth's going out to our sub-circuits, into our sockets and lights and stuff need to work. We haven't covered yet all of the stuff around earthing, like what is earthing, what is it for, how does it work, but nevertheless, if we need any information about earthing, this is the section that we go to. Hopefully you're starting to build a picture now that each section covers a specific thing in relation to an installation. So if we need to know more about earthing, or we're confused about how we're going to do the earthing in an installation, what size conductors we need to use, all of that sort of stuff, this is where we go. Section 5, earthing. Section 6 will be damp situations. So damp situations are any place where there's going to be water present, just in the general nature of that place. So a great example is bathrooms. It's the most important one that we would deal with. Kitchens as well. So the requirements for electrical fittings, cables, in a damp situation such as a bathroom may be a little bit different to how we would do that outside a bathroom. For example, you probably don't want a socket sitting right next to a tap, because water and electricity don't mix. Well, water and electricity do mix, but only in incredibly dangerous ways. So Section 6 gives us some special requirements for damp situations. Now, as I said, bathrooms are probably the primary one there. That's reasonably simple. If you go and have a look at that section, what you're going to find is a lot of diagrams. So it's going to cover things like spa pools, outdoor pools, all of that sort of stuff. And there's lots of diagrams that tell you how far away from the bathtub or the basin or the shower that you need to have your light switches and all of that kind of stuff. So it does get fairly dense and complicated in that one. The general rules are fairly easy to remember, but if you want to get more specific, then this is going to be your it's going to be where you're going to look. And as I say, it does get fairly dense and complicated. So nobody expects anybody to really remember that stuff. I guess some people out there do if they do this all the time, but most people, I would say, if you're putting, some sort of, if you're wiring up, for example, the water pump for a pool, this is where we want to look, because we're going to need to know what do I need to do to make sure that is safe. Section 7 is special electrical installations. So it's the minimum standard in relation to the selection and installation of equipment in special electrical installations. Let's just go and have a quick look at that one, because I can't remember off the top of my head what falls under special installations. So let's see, that will be section 7. We have it here. So if you look at all of these ones here, so this section is going to give us the rules around, as I said, special electrical installations, and this defines what those special electrical installations are. So electrical systems for safety services, generators, extra low voltage, which is alarm systems, fire alarms, security alarms, those kinds of things. High voltage electrical installations where an explosive hazard may arise, which is like your service stations, your dairy factories, we've talked about that before, vapor and dust hazards and so forth. So if we just scan down to one of those, let's have a quick look, because what it will probably tell us is that we need to refer to a separate standard. Let's find one that I know there is other standards. Okay, so hazardous areas. So this here is going to give us some detail on how we build electrical installations in hazardous areas. But you'll notice here that it actually refers us to a separate standard. So talking about classification of hazardous areas, where we need to know what kind of area it is. So this tells us where we're going to go and have a look. ASNZ 60079.10.1 for gas or vapor, or 60079.10.2 for combustible dust. So it's two slightly different sets of rules depending on the type. If we look here at electrical equipment, so selection of electrical equipment, so this is going to tell us the rules around what sort of equipment that we can use within a hazardous area. And what does it say? Electrical equipment selected for use in hazardous areas shall comply with the appropriate requirements as specified in ASNZS 60079.14. So even though within this standard ASNZS 3000, it does in section 7 give us rules around specific special installations, as we just said, it's actually going to refer us in the first instance to another standard, ASNZS 60079, which is the standard for hazardous areas. And you'll find if you go through section 7 and you look at each of those different types of installation, it's going to refer to those. And again here, if you see it 7.8 specific electrical installation standards, here it gives them to us here. So construction and demolition sites has its own standards, 3012. Transportable structures and vehicles, including their site supplies, so that's like caravans, camper vans, that kind of thing. It says we go to ASNZS 3001. So in the first instance, if we're doing that kind of work, we can go to ASNZS 3000 and see what it says. But in most cases, it's now going to tell us go to this standard, and we'll deal with those standards specifically as we go through the course. I think module 4 or 6 maybe, we actually do a topic on each of those individual standards. Section 8, verification. So this is probably for us, at least in our initial stages, the most important one. So section 8 gives us the standards for inspection and testing that must be achieved to satisfy the fundamental safety principles of part 1, so on and so forth. So when we've completed building our installation, this tells us how to do the inspection and testing, section 8. For example, some of the work that we've already done, the practices we've done on isolating and reconnecting a fixed wired appliance, this section 8 of ASNZS 3000 is the place that we would look to find the information. How do I need to test that? What are the legal requirements for testing? Why is that important? Because I think I've said it before, you can do all sorts of shady stuff, but as long as you test properly, you know that things are going to be safe. I'm not saying do shady stuff. What I'm saying is when we test and inspect, if we do our testing and inspecting properly, it'll tell us whether we've done something shady, because if we pass all the tests, then we know that things must be safe. So we're going to delve into section 8 a little bit more, because as I said, it's the most important one, at least for us now. So section 8.1.2 says, prior to placing an electrical installation or any part thereof in service following construction, alteration, addition or repair thereof, it shall be verified as far as practicable that the installation is safe to energize and will operate correctly in accordance with the requirements of the standard. Whew. A lot of words, and all it's saying there really is once we've finished building something or altering it, changing it, whatever, so if I put in a new circuit or I build a new installation, whatever, this is saying that after I've done that work, I have to test it to make sure that it's safe. Pretty simple. To confirm that the requirements of the standard have been met, after completion, so after I've finished work, but before being placed into service, so before I turn the power on, the installation shall be inspected as far as practicable. Practicable, we've come across that word in relation to the Health and Safety at Work Act. Again, it means essentially the same thing. It means that doing all the things that I can reasonably be expected to do. An example of something that would not be practicable is that if I go to a new house and I do all the wiring, I put all the wiring in the walls before the walls are on, so just framing, and I know that it's all safe and everything's good because I've done it. When I come back to do the fit off and then test it before I turn it on, presumably the walls have been put on, I can no longer see those cables. So this part of the standard does not require us to then go and rip all the walls out so I can look at the cables before I turn it on. It allows us to assume that if the cables were good when we put them in, we assume that they're good now. They may not be. Hopefully, if they're not, an example might be if one of the jib stoppers stuck a nail through one of our cables, something like that while we weren't there. Hopefully we pick that up when we're testing. But again, it does not require us to rip all the walls off so that we can prove it, because that would not be practicable. And B there says tested in accordance with clause 8.3. So before we turn anything on, we have to test in accordance with section 8.3. Precaution should be taken to ensure the safety of persons and to avoid damage to property and the electrical installation equipment during inspection and testing. So while we're testing, we shouldn't do anything dangerous. Section 8.2, visual inspection. A visual inspection shall be made when work on an electrical installation has been completed in order to verify the work complies with the requirements of the standard. So visual inspection is exactly what it says. Go and have a look. It may not sound like testing, right? Testing is something that we do with meters and we get results and we write them down and it's all very clever. But a visual inspection, in a lot of cases, is probably our most important one. What would we cover in a visual inspection? We need to check that we've connected the right conductors to the right place. Is the red wire going to the right place? Does the black wire go to the right place? That's a really easy way for us to pick up if there's any faults, right? I just go and have a look. I look at all the sockets and go, are they in the, yep, they're in the right place. That one's in the right place. I can go and look in the switchboard and make sure, is all the power going through the main switch? Are all the green wires connected to the earth bus bar? You know, that kind of thing. So visual inspection, while we kind of take it for granted, and I guess in a way while you're doing the work, you're kind of completing your own visual inspection, but it is a really important thing that we need to do. We move on to section 8.3, which is the most important one. Testing. After completion of or in association with the visual inspections that we've just done, tests in accordance with 8.3.3 shall be carried out on the installation to verify it complies with the requirements of the standard and that is suitable for the use intended. Okay, so we have to do tests. It tells us we have to do testing. What tests do we have to do? Well, it tells us here everything that's contained in clause 8.3.3. So let's find 8.3.3. Here, surprise, surprise, here it is. So mandatory tests. These are the ones that we must do on any work that we do. Continuity of the earthing system. It's the earth resistance of the main earthing conductor, protective earthing conductors and bonding conductors. So we probably don't yet have much idea what an earthing system is, or how it works, or what it's for. What I can tell you in very simple terms is the earthing system is all the green wires, and that's one about the earthing system, without going into too much detail, is one of our primary safety systems within an electrical installation. So we need to know that that safety system works. How do we do that? We need to test that all of those conductors are continuous. That means that they're connected at one end and connected at the other, and that we have a good circuit in between. An example of not continuous would be if somebody had cut one of those wires. So if I test the earth wire at the socket and I test the earth wire at the switchboard, I should have a circuit in between. There should be one continuous wire running through that. If I do that test and that is not a circuit, or the resistance is too high, then I know something has gone wrong. There's a fault in there. So I need to test the continuity of every earth wire inside an installation. And there's a table in section 8. If you want to go and have a hunt around and find that, it might be table 8.1 or 8.2. I can't remember off the top of my head. But that tells us what the resistance values should be for the earthing system, depending on the situation, size of the cables, all of that kind of stuff. Again, we get into much more detail on earth testing later on, but that's it in basic terms. Our second mandatory test is insulation resistance. Third is polarity. Fourth is correct circuit connections. Fifth is verification of impedance required for automatic disconnection of supply, which we call earth loop impedance, or earth fault loop impedance, and operation of RCDs. So a little bit more detail on each of those. So as I just said about the earthing system, we need to test the continuity. Test to prove the continuity, that is a continuous wire from one end to the other, of the earthing system are necessary to ensure the earthing system has been installed in a manner that it will cause circuit protective devices, that's our fuses and circuit breakers, to operate if there is a fault between live parts other than the neutral and the mass of earth. An effective earthing system will ensure that exposed conductive parts of electrical equipment do not reach dangerous voltage when such faults occur. Again, I'm not going to get into the detail of what all of that means. It will be here literally all day. But the short answer is, as I said before, we need to test that the earth system, all of the wires in the earth system are continuous and have a nice low resistance, because that's our primary protection system. It means that if a phase wire, a live wire, contacts any of my earth wires, it's going to cause a short circuit, and that should blow the circuit breaker. I want that to cause a short circuit, because that's going to trip the circuit breaker and therefore turn the supply off. So if any earth conductors come in contact with anything that I might touch, so if any live conductors come in contact with anything I might touch, then it should cause a short circuit and blow the circuit breaker, which is a good thing. If it didn't blow the circuit breaker, then when I touch that thing that the phase conductor is touching, then I will get a shock. Okay, insulation resistance. An insulation resistance test is necessary to ensure the insulation resistance between all live conductors and earth, or, as the case may be, all live parts and earth, is adequate to ensure the integrity of the insulation. This is to prevent electric shock hazards from inadvertent contact and fire hazards from short circuits and equipment damage. In addition, an insulation resistance test between conductors is necessary for consumers' mains and submains to minimize potential for insulation breakdown, injury, or property damage because of a failure of such conductors. The integrity of the insulation is stressed by applying a direct current at 500 volts. Right, what does all that mean? Okay, insulation resistance might be the most difficult test for you to understand. Let's see if we can pull it off. What we're going to do, if you imagine a cable, imagine a length of TPS. That's the flat white cable with 3 wires inside it that we've probably seen before. If there's any breakdown of the insulation between 2 of those conductors, let's say the red one and the black one, if they're touching, that's going to cause a problem for me. I'm going to cause a short circuit. Bad things will happen. I definitely don't want that. As I said before, if somebody's put a nail through a cable, they might have stabbed a nail, and that the nail itself might join the red and the black wires by penetrating both of them, or a staple or anything like that. Or maybe poor installation practices by me. Maybe I've accidentally nicked the conductor and 2 of them are touching. So how do we prove that they're not? I mean, I can't see inside the walls. I certainly can't see inside the cables themselves. So we're going to need to do a test. What we're going to do is we're going to put a voltage on the red wire and a voltage on the black wire. We use a special meter to do this called an insulation resistance tester. I put a voltage on each of them, and if there's any touching between their red and black wire, then the insulation resistance tester is going to show me that there is a circuit. Just like we did with the earth continuity, but this is the opposite. When we do earth continuity, we want a circuit. It has to be a very low resistance. With insulation resistance, I'm testing between 2 wires that shouldn't be touching, and so therefore I should find that there is no circuit. Now, insulation works. Everything that is an insulator could theoretically be a conductor, as long as the voltage is high enough. Like I think I've said before, air is an insulator. We use air as an insulator for power lines. The power lines aren't covered by any sort of insulation, but we just have air between them. The air is acting as insulation, and the theory being, if I don't touch that wire, I can't get a shock from it. But we know that lightning exists, and lightning What is lightning? That's electricity physically being conducted from the clouds to the ground. So in that case, air must be a conductor. Well, how does that work? Well, if we raise the voltage enough, and in the case of lightning, we're talking about many thousands, hundreds of thousands, perhaps even millions of volts. Once the voltage gets high enough, it can break that insulation, in this case the air, and conduct. So we can see from that example then that the higher the voltage, then the higher the chance that the insulation can become a conductor. So if we have a small fault in our insulation between two wires, at the kind of voltage that my multimeter will put out, which is like 1.5 volts, the voltage of the battery, I'm not going to really test that insulation very much. And if I had a very slight fault in there, that meter might not pick it up. So what we need to do is put a higher voltage on it. When we connect it to the power supply, for example, it's going to have 230 volts on it, right? We know that. So we at least need to know that the insulation is going to protect us if we've got 230 volts. Well, in fact, we're going to go a step further than that, and we're going to test it with 500 volts. The idea there is if the insulation is good against 500 volts, then it's definitely going to be good against 230 volts. And again, when we're talking about stressing insulation, if we go back to our example of water in a pipe, the insulation, in this case, is the pipe itself. So insulation breakdown or faults in the insulation or anything like that is the equivalent of a leak in that pipe. If I've got a hole in my pipe, the water's going to come out. That makes sense, right? If we think about that voltage, as I said before, that the voltage can break down the insulation. Voltage, remember, in our water example was pressure. So what we're saying is, what does that mean? The higher the voltage, so higher the pressure in my water pipe, the more chance that it's going to leak. That makes sense, right? If I have a very tiny pinhole in my pipe, but I don't have much pressure in there, not much is going to leak out, and maybe none at all. But if I ramp that pressure up, if I start really pushing that pressure, it's going to do two things. Not only will it leak out faster, but potentially it's going to start to make that hole bigger. And with insulation resistance, it's exactly the same thing. If I have poor insulation, the higher the voltage is, the more chance that it's going to jump out of that hole to somewhere that it's not supposed to be, like to me or somebody else. And also when we get that really high voltage, it could start to break down the insulation itself. That's where it makes the hole bigger in the pipe with the bigger pressure. So we're going to test with a higher voltage than we are ever going to see on that circuit to make sure that it's good. If it operates okay when we test it at 500, then it certainly should operate at 230 volts. Hopefully that makes sense. So we use 500 volts. So we have a special tester. It's called an insulation resistance tester. It will output 500 volts, and that is the requirement. For anything that's going to be connected to a normal power supply, 230 volts, we must test it with 500 volt with a 500 volt meter. Do not try and test insulation resistance with a multimeter. If there was a short circuit, you will find it, but if there's just a small fault in the insulation, you probably won't. One question that people always ask me when they see someone in the class is thinking of this now, and if you are, you're very clever. They're looking at that going, a 500 volt meter, isn't that dangerous? Would that give me a shock? And the answer is yes it will. Is it dangerous? No, because there's not enough power behind that 500 volts to actually physically hurt us. Will it hurt? Yes. It's like getting a shock from an electric fence. Well, it's much smaller than that. It's like a bad static shock. So if you take the insulation resistance tester and you grab the two probes, you push the test button, it's going to give you a 500 volt electric shock. As I said, there'll be very little current there, so it's not going to harm you, but it will hurt. It's like getting a bad static shock off a trampoline or a car or something like that. And then the next question that you're going to ask, if you're anything like me, is can I try that? And my answer is no, you cannot try that. I do not give anybody permission to shock themselves or anybody else with 500 volts from the insulation resistance tester. Are you going to do it anyway? Almost definitely somebody out there is going to do it. It's just human nature. That's what we do. When I was an apprentice, did me and my friends try to prank each other by coming up with clever ways that we could shock each other with the insulation resistance tester? Yes, we did do that. Am I recommending that you're doing it? Please don't do it. Not in my class anyway. If you're outside of class, do what you want. But I'm telling you, don't do it. Don't do it. There's no value in it. You're just going to get a shock and go, ow, that hurt. All right, moving on. Polarity. So polarity is ensuring, or polarity means specifically that the phase is phase and the neutral is neutral. So there's my polarity. So I need to test, for example, testing polarity would mean that making sure that the phase terminal on a socket is connected to the phase wire and the neutral terminal is connected to the neutral wire. So polarity testing is necessary to ensure that no shock hazard arises from the incorrect connection of active, neutral and earthing conductors. So if I switch them around accidentally somewhere along the way. This testing is to prevent the transposition, so switching, of active and neutral conductors of the consumer mains or submains, supplying an outbuilding having an MEN connection, resulting in the electrical installation earthing system becoming energized. Right, so our earthing system is going to be connected to all the metal parts of an installation. So if you've got a metal bench, that'll be connected to the earthing system. The idea is that if somehow that metal bench got live, the earthing system will provide a path back to neutral and therefore trip the circuit breaker. So by the time I come along and touch the bench, the circuit breaker has blown and there's no voltage there. If your main supply coming into the building accidentally gets transposed phase and neutral and all my earths in the system are connected to the neutral, then I actually might liven that kitchen bench accidentally. Think about it. The phase coming in gets connected to the neutral part of my installation instead of the phase. It's actually transposed. That neutral is connected to the earth. The earth is connected to all of the metal parts in my building. So now my metal kitchen bench is now connected directly to the phase. This is very bad, very, very bad. And it's easy to do. It can be tricky to work out which, I know this sounds crazy, but it can be tricky when you have a supply coming in from the street or power lines. It can be tricky to work out which one is phase and which one is neutral. Why? Because if I test between the two, it tells me there's 230 volts. If they weren't colored, how would I know which one is which? I can test it any way I like. I still only know it's 230 volts. So polarity testing needs to be done physically to earth. So if you see the line mechanics, when they do connections at the pole, they will actually stab a post into the ground with a wire running off it, and then they can test between that wire and each of the conductors to tell which one is which. But it still happens from time to time. Line mechanics get lazy and they don't do that test. They just look, oh, yeah, that must be the live, that one must be the neutral, and every now and then you'll hear about an incorrect connection where the mains is coming into the building. We usually don't do that connection. An electrical inspector would do that connection, so they would generally be responsible to test whether the active and neutral conductors are coming to the right place. But we can also do that test. What else? Combinations of incorrect active, neutral and earthing conductor connections resulting in the exposed conductive parts of the electrical installation becoming energized. So this is the same thing, that if we accidentally connect the phase and the neutral around the wrong way, somewhere other than the switchboard or the mains coming in, so somewhere in the installation, we could accidentally connect live power to metal parts in the installation. Again, let's use that kitchen bench as an example. If I accidentally connected something in my house the wrong way around, I could potentially put live voltage on that kitchen sink. And third one, that the connection of switches or protective devices in neutral current conductors resulting in parts of appliance such as heating elements or lamp holders remaining energized when the switches are in the off position, and multi-phase equipment such as multi-phase motors and semiconductor controlled equipment operating in an unpredictable manner. So that means if you think about a light switch, I have a circuit running, phase wire, light switch, light, back to neutral. When I wire up my light switch, if I switch the live and the neutral, it will still work. I still have a circuit path, a switch, a light, and a return path. There's no issue there. Physically, in terms of its ability to work, if I turn the switch off, it's still going to break the circuit. If I turn the switch on, it's still going to allow the light bulb to go. So phase and neutral won't change, or it doesn't matter if I change the phase and neutral from an operational point of view. What I don't want to do, if I switch If I put my switch in the neutral conductor instead of the phase, then that means when I switch that light switch off, I'm breaking the neutral conductor. So everything on the phase line is still live up to that switch. That means that I will have live voltage at my light. The light won't be going, but there'll be 230 volts there even though the switch is switched off, because the switch is in the neutral instead of the phase. So that could cause someone to get an electric shock when they're changing a light bulb, for example. So we need to always check, and this is part of our polarity testing, that our switches are switching in the phase conductor and not the neutral conductor. We will see this a little bit more. It's probably quite a difficult concept. Some of you will pick that up fairly easily and understand what I'm talking about. Some of you might find that quite hard to understand. We'll be able to see what that means when we do a bit more practical stuff. When we start getting into wiring up circuits, you'll see what I'll be able to explain what I mean by putting the switch in the phase conductor and not the neutral. Verification of impedance, so the earth fault loop impedance. Socket outlets not protected by an RCD. Where an installation includes circuits containing socket outlets not protected by an RCD, the impedance required for automatic disconnection of supply shall be verified on each such circuit by verification of the total resistance of the active and protective earthing conductors. Where a supply is available, that's where it's switched on, verification of the earth fault loop impedance in accordance with clause 8393. Okay, we need to know a lot more information than we currently do to be able to really figure out what the earth fault loop impedance is. But very shortly, it means that our circuit breaker and a switchboard is our primary safety device. If I put too much current through that circuit breaker, more than the rated current, so you can get a circuit breaker for different settings. It might be 10 amps, 20 amps, whatever. So let's say a 20 amp circuit breaker is very common. If I put more than 20 amps through that circuit breaker, it should trip. So if I have a short circuit on that circuit, then I should get a very high current and the circuit breaker trips, which is good. Because if I don't trip that circuit breaker, then we're going to get that short circuit. Maybe hundreds of amps are going to flow in that circuit continuously until something in the circuit burns out, like the wire itself. And that will cause heat. It may cause a fire. It's really bad news. So we need to make sure that if we get a short circuit, the circuit breaker will trip. That makes sense. Now, so how much current is going to flow in that circuit when I have a short circuit? If I touch the red and the black wires together, how much current will flow? Well, that depends. It depends on the resistance. We've very briefly touched on this, that current is voltage divided by resistance. So the higher the resistance, the lower the current flow will be. But I definitely need to have a high current in there, otherwise the circuit breaker is not going to trip, which is really bad. So what we need to do is test what the resistance of that circuit would be. What is the resistance of that whole wire all the way back to the point of supply in the event of a short circuit? Now again, how we do this and all of the stuff around it's not worth going into now, but what I can tell you is an earth fault loop impedance test is a test of what is the total resistance in that circuit, how much current is going to flow if there's a short circuit, and then I can use that to work out, am I getting enough? Is this going to be enough to blow the circuit breaker? Again, we use a special tester to do this, and it's pretty simple. You plug the tester, it physically has a plug on it, you plug it into the socket, you select the correct setting, and you push the button, and it'll tell you the answer. Very good. We'll do lots of earth loop impedance testing throughout our course, so this will become more and more familiar to you as we do it. If you got to this point of the video so far and you're thinking, I don't understand anything that he's talking about, I don't understand what earth continuity is or insulation resistance or earth loop impedance, don't worry. I'm trying not to give you too much detail because I know that we don't have the required background knowledge for this to really make sense. If it's kind of making sense to you, or if you're understanding that I have to do some tests and this is what they're called, and here's a kind of rough idea of what each of them might be for. That's enough. That's don't freak out. If you are freaking out, give me a call. Give me a call. We can talk through it. Anybody who wants more information on this, if you want to chat to me and we talk for an hour about what earth fault loop impedance actually means, I'm more than happy to do that. But don't worry, this is not the only time that we will cover this. We will do this constantly and continuously. Testing is probably the thing we do the most of over this course. So you'll pick it up as we go along. Operation of RCD. So an RCD is another type of safety device. We talked about circuit breakers very briefly. An RCD is another safety device. I think we've mentioned before that you get portable RCDs on extension leads. These days, it's the requirement that any new sub-circuit that's installed or any new build must have RCDs protecting everything. So we're going to see RCDs a lot in switchboards. So when we install an RCD, we need to test that RCD works, and that's RCD testing essentially. Again, without going into too much detail, the RCD has an advantage over a circuit breaker because an RCD can trip at very, very low currents. So it can pick up whether there's a small fault current in a circuit and it'll switch off. That small fault current in the case of RCDs in New Zealand is generally 30 milliamps. That's the requirement. So it must be able to detect a fault current of 30 milliamps, and it must switch off within 400 milliseconds. So 400 milliseconds being 0.4 of a second. So very tiny current switches off very fast. Again, we're going to use a special meter, an RCD tester, and we connect the RCD tester to the RCD, and we push the button, and the RCD tester will trip the RCD, and it will measure how much current did it take and how fast did it trip. At a very basic level, we don't need to know any of that information at all. All we need to do is plug it in, push the button, and decide whether that is a pass or a fail. We will, again, further on in the course, we'll get into great detail about how an RCD operates and what's actually happening when we run that test. But for now, what we need to understand is that we use a special meter to do that, an RCD tester. We plug it in, we select the right function, push the button, and it's going to tell us a specific piece of information. It's how long it's taken to trip, or how many milliamps it took to trip it, or something like that. And then we should know, we'll learn later, or what are the requirements, how fast should it be tripping, how much current, all of that kind of stuff. Okay, let's move on to AS/NZS 3760. So AS/NZS 3760 is primarily concerned with the testing and certification of appliances. In-service testing is a necessary part of any safety program to help ensure the safety of persons using electrical equipment in the workplace. Key phrase there, the workplace. This does not cover appliances used in your home by yourself. Those don't have to be certified. You can be as unsafe as you like with your own stuff. This standard specifies in-service safety inspection and testing protocols and criteria that satisfy these obligations, and provides a cost-effective approach to safety without jeopardizing personnel safety or involving excessive equipment downtime. So it's there to give us to tell us how we need to test things, and so that we can do that in a way that's not going to cause a lot of drama. Like, we're not going to have to send everything in the workplace out to some specialist safety organization or anything.